Hey guys, today's problem is called stack. We have to design stack that supports push, pop, dot, and retrieving the minimum element in constant time. So this is a classical problem of enhancing the data structure. In this case, besides the common operation that we have on the stack, we also um, are retrieving the minimum element, and we have to do it in constant time. So we have to implement the min stack class, initialize the stack object. Push and pop are basically the same as we would have in a normal stack. Get the top of the element of the stack for the top. Pop just retrieves the element on the top of the stack, and push pushes the element onto the stack. Now the special function is get min, which returns the minimum element in the stack. We have to implement the solution with constant time complexity for each function. Now we are given here an example, but we will go through an example by hand just to see how the stack should behave. Let's just go scroll down. Now for the constraints, nothing special. The value is between the minimal integer value and the maximum integer value, and always the method stop and pop and get min will be applied to a non-empty stack, so we don't have to care about that. It would be a good question for the interviewer to ask if we should implement exception or something if the stack is empty and we are calling this methods on top of it. Now, to solve this problem, we know that we can just basically use stack to mimic everything that we have as requirement, pop, push, and peak or top. We can just use a normal stack. But for example, if we have 1, 2, 3 as the elements that we are pushing to the stack, the stack will look like this: 1, 2, 3. And now to find the minimum value, we would basically have to traverse through the stack, which basically means discarding all the elements and then inserting them again. And while we are discarding them, while we are popping them out, we would be checking if we if the current minimum that we have found is still the minimum. If we have, for example, if the current top of the stack is 3, we would discard this element and declare our minimum as 3. Then we would compare 2 with 3, and because 2 is lesser than 3, we would set our minimum to 2. And then again for the number 1, we would do the same. We would discard number 2 as a minimum and put the minimum as 1, because that's our minimum value from the stack. But there's an easier solution. Instead of just pushing the elements as they are inside the stack, we can push a pair. And that pair will basically be the value. Just basically, if we are pushing number 3, we will be pushing the same value, so the raw value, and also the minimum that we have at this point. So let me show what I think by that. So for example, if you are inserting number 1, there's nothing in the stack, so number 1 will be the minimum. So in the stack, we will insert number 1 and the minimum, which is again number 1. Then if we are pushing number 2, we will again push number 2 just as it is, but then we will compare it with the current minimum. And the current minimum is just, we can just find it by checking the current top element and current top pair actually, and retrieving the value for the minimum. Now in this case, it's 1, and 1 is lesser than 2, so the minimum for this pair will also be 1. The same goes for number 3. Now when we insert number 3, we will just insert it as this for this part of the pair. But for the minimum part, we will check the top element and see that their pair is 1 at the position of the minimum value. The value is basically just 2. So we will see if the number 1 is lesser than number 3. In this case, it is. So this is the minimum. Now, if you are pushing, for example, minus 1, we will push it as it is, but then we will compare it with the pair that we have at top, actually the mid value, which is 1. And because -1 is now lesser than 1. It will be inserted as a pair with the value -1, but the minimum will be again -1, not 1. So the next time when we search for the minimum, we will just check the top element and retrieve the value which is -1, which is also the minimum value of all the elements that are inserted into the stack. So the trick to the question is just, instead of inserting only the raw value that we are getting as an input, we will also be calculating the minimum and putting it as pair. We will be pushing it as a pair to the stack, and we will be getting the minimum by comparing the current number that we are pushing to the stack and the minimum value so far that we can just retrieve from the top element of the stack. Next, we will solve the problem using Java programming language. We will first declare our kind of top tuple class, which contains just the value and minimum, and this will serve as our pair that we will push into the stack. We will declare our private value, which is a stack containing value min pair elements. And we will initialize it to an empty stack inside the constructor. For push inside, if the stack is empty, we will just push the raw value, and also for the minimum, because the element that we're pushing is the only element inside the stack, the minimum will be the element itself. If not, we will be pushing the raw value of the element, but checking if the value that you're pushing is either smaller or larger than the current minimum. And we get that minimum by using our function get min, which will just check what's the current min field of the pair that's sitting on the top of the stack. For pop, we will just use the stack native implementation of a function pop. For the top, we will just use the implementation of the peak. And now for the get min, we will just peek the element at the top and get the field min to get the minimum value. And as you can see, all the functions we have implemented have constant time complexity. We only have additional space complexity for the stack that we have to reserve, that will be the underlying data structure for our enhanced min stack.